Alright, so we will apply a differentiator to a stochastic process x of t. So let's say x of t has autocorrelation function rxxt1 t2, which is expected value of xt1 xt2. So if you want to find out x prime t1 t2, that's by definition expected value of x of t1 and x prime t2, but x prime t2 is expected value of x of t1 derivative with respect to t2. So if you pull the derivative outside, you get d by dt of expected value of xt1 xt2. But so this is rxx t1 t2. So this is d by dt of rxx t1 t2. Now similarly, if you want to look at the output autocorrelation function, so that's expected value of x prime t1 x prime t2. So if I write this explicitly as derivative with respect to t1 of xt1 x prime t2 and pull the derivative outside, then we have expected value of x of t1 x prime of t2, but that's rxx prime t1 t2, so this turns out to be d by dt1 of rxx prime t1 t2. So together we have these results. Rxx prime t1 comma t2 is derivative with respect to t2 of rxx t1 t2, and rx prime. So this is the cross correlation and the output autocorrelation in terms of the input autocorrelation. So this is dt1 dt2 rxx t1 t2. Now if you assume the input process is also Whiteson stationary, then we can replace this t1 comma t2 by t1 minus t2. So if I make this variable tau, so t1 minus t2 is tau here. So variable is here t2, so minus d2 is d tau. So from there you get rx x prime. So this is tau, so the right side is only a function of tau. So the left side is also a function of tau, but now it reads rxx tau. And same thing here, so this is a function of t1 minus t2. I'm sorry, here it's a function of t1 minus t2. So here t1 minus t2 is tau, and the variable is t1, so dt1 is d tau. So this would read derivative with respect to tau of rxx prime tau. So this is also Whiteson stationary. So if I put it together, this reads x prime tau is minus the second derivative of rxx prime rxx tau. So if you want, you can write this symbolically in this fashion. And this is a non-negative definite function. So as a simple consequence is that if you look at rxx prime tau here, so in this expression, if you replace a tau by minus tau everywhere, you get rxx prime minus tau is minus tau, minus minus plus, minus tau. So this becomes p by d tau of rxx minus tau. And if the process is a real process, then this is the same as rxx tau. So but on the other hand, this is minus of xx prime tau, because if you look at this, this is just this expression is minus of that. So from here you have Rx x prime tau plus Rx x prime minus tau is 0. So from here, of course, it would mean Rx x prime 0 is 0, put tau equal to 0. But this literally means expected value of x of t and x prime of t is 0. So these two random variables are orthogonal. And since x of t is Whiteson stationary, it has constant mean. So the mean of x prime is 0. That means x prime is mean is 0. That means these two random variables are uncorrelated. X of t and x prime t are uncorrelated. And if they are Gaussian, of course, x of t is Gaussian, then x of t and x prime t are point-wise independent. Not the entire process, but point-wise. So we can use this as an application to quickly solve for the level crossing problem, to get an idea. So in other words, if we want to find out what is the probability of, let's say x of t is a Gaussian process, zero crossing probability. So this is an up crossing here. So if I define a rho to be the up crossing rate, so the probable up crossing probability rate, then up crossing will happen if at t the function has to be negative, and at some t delta t later the function need to be positive. So let me call this random variable to be x1. So we want x1 to be negative and x of t plus delta t to be positive. So x of t plus delta t is x of t plus x prime t multiplied by delta t. Of course, this is what we are calling x1, and then we call this to be x2. So x2 clearly need to be positive. This is negative and you want this whole thing to be positive. You want x2 to be positive. That means x1 has one more condition. x1 need to be greater than minus x2 delta t. So notice that consequently this probability that we are looking for can be written as joint density function of x1 and x2. And x1 goes from minus x2 delta t to 0 because x2 need to be x1 need to be negative. Right here, this is x1 need, and x2 on the other hand is the derivative which needs to be positive. This density function will split up because we just proved that in the Gaussian case x1 and x2 are independent. So we have to copy that expression, we have delta t is integral 0 to infinity. So you have f x2 and x1 goes from minus x2 delta t to 0 f x1 dx. Now if I take the derivative with respect to delta t, I get rho. Here, this is all independent of delta t. So the derivative of top limit is 0, derivative of the bottom limit is minus x2, minus minus plus. So there will be an x2. Then evaluate this function, evaluate the integrand. So this will turn out to be minus x2 delta t plus the third term, which is the derivative of this with respect to x2 delta t is 0. Now this is an equation where delta t is very small. So if you push delta t to 0, you will get the limiting case, the rate. So the rate is going to be integral 0 to infinity. Let me substitute for, so this is 1 over square root of 2 pi sigma 2 squared e raised to minus x squared by 2 sigma 2 squared multiplied by x2 multiplied by square root of sigma 1 squared, because fx1 of 0, this goes to 0, is this value dx2. So if I pull out the constants outside, this now reads sigma 1 sigma 2 integral 0 to infinity x2 e raised to minus x2 squared over. So if I substitute this by y, just y, so notice that dy is going to be 2x2, so 2 cancels, x2 over sigma 2 squared, or x dx2 is sigma 2 squared multiplied by dy. So this can be replaced by sigma 2 squared integral 0 to infinity e raised to minus y dy. Integral answer is 1. 1 sigma 2 cancels. So you get the rate to be 1 over 2 pi sigma 2 over sigma 1. But in terms of autocorrelation functions, sigma 1 is what? Sigma 1 is the variance of the random variable x1. x1 is x of t1. So that's variance is rxx0. So that's rxx0. And sigma 2 is the variance of the random variable x2, which is the derivative of x of t. Its variance is rx prime x prime evaluated at the origin. But rx prime x prime is, we have it here. Rx prime x prime is minus the second derivative. So if you want, you can also replace this expression as 1 over 2 pi square root minus rxx0, and numerator you have r double prime xx evaluated at origin.